This video is going to cover some titration stuff. This is page 5, I believe, of your notes, and I will cover probably page 7 also, just for the sake of time on this video. So here's some titration curves. Remember, titration is usually you have a solution such as, in this case we're adding base. So what we have here is we have a flask with acid in it, adding base with a burette. Okay, so remember, in the past, it's always turned pink because that's the indicator we've chosen as turned pink at what's called the equivalence point. So maybe you know this concentration, or maybe you know this concentration. You can figure out the other concentration based on how much you have to add to get to the equivalence point. So here's our first one, the strong acid, strong base titration. So if that's the case, strong acid, strong base, that's going to make water when you get to equal moles of them. Obviously, if you put too much of one or the other one in, you will not have that. So strong acid, strong base, pH will be 7 at the equivalence point. So equivalence point means when you have equal moles of acid and base. So stoichiometrically equal number of moles, acids, and base. The indicator we'd use, you want to change somewhere close to 7. So the end point of a titration is when your indicator changes color. Hopefully your end point is approximately the same time as your equivalence point. It has to be really, really close to it for it to be good titration. So there are several acid-base indicators that change colors at different pHs. Bromoethanol blue goes from yellow at a 6 to blue at a 7.6. So it would change in this range and work pretty well for that titration. If you look at these curves, remember this is showing pH. And this is how much of the base is being added in this case. Now it could be acid being added, which would make your curve go down. So don't let that confuse you when we have pH, we have curves like that. Weak acid, strong base. The strong base is stronger. So at the end of this, you'll actually have a weak base. So at your equivalence point, you're going to have a weak base right here, and your pH is going to be greater than 7. So maybe around an 8 or a 9, somewhere in there. Your pH will be greater than 7 when you do this curve. So phenolphthalein is a good one with that. We've used before. It turns pink. Goes from clear at 8.3 to pink at a pH of 10. Strong acid, weak base. In this case, the acid is stronger. So when we have equal moles of these, we're actually going to have a weak acid. And your pH will be below 7. So maybe a 5 or a 6 at your equivalence point, somewhere in there. Methyl red is a good one for that. It changes 4.6, it's red. 6.2 pH, it is yellow. So different indicators. We'll talk a little bit more about titration curves as we go through there. But your equivalence point is kind of the middle of the steep part of the curve. So again, pH, how much you're adding of the titrate. In this case, is a base. It could also be an acid, and this could be a base down here. We're going to do a strong acid, strong base titration. There are 2 pages in your notes about that. One of them, this is page 6 of your notes. It's kind of done for you, so if you need to follow an example, want to see what's going on, it shows some ice tables here, essentially, and how stoichiometry works with strong acid, strong base. I'm going to do the page after that. It says you try it. So we're going to do this page where it does not give you the information, at least doesn't give you all the work. So here's what you have here. You have 40 milliliters of 1 molar HCl is titrated with 4 molar NaOH. So in here, in the burette is your 4 molar NaOH. Okay, we have plenty of milliliters of that we can drop in. In our flask down here, which I'm going to draw a little bigger. In our flask down here is our HCl, and it is 1 molar. And we have 40 milliliters of the HCl in there. All right. Again, it is strong acid, strong base. Let's write the equation. Strong acid, you only write H plus. Strong base, you only write OH negative. So if we think about our reaction here, our reaction is just H plus OH negative equals H2O. So we think about at the equivalence point, when we have equal moles of hydrogen ions, equal moles of OH negative ions, when those react equally, they're both limiting reactants, we now have water. So at our equivalence point, our pH will be 7 when we have equal moles of those. So things I always like to figure out right away. First thing, let's figure out how many milliliters of this do we need to add to get to our equivalence point. Well, the reaction, everything's a 1-to-1 ratio in terms of moles if we write this out. So if this is 4 molar and this is 1 molar, this is 4 times as concentrated, so we need 4 times less milliliters to reach the equivalence point. Well, this is 40 milliliters, we'd only need 10 milliliters. Or we can do a little MV, which is what most students have done. So if we do MV for our base, we're going to have 4 times V equals MV for our acid 1 molar times 40 milliliters. Remember, this just means moles equals moles. Molarity times volume is moles. Sorry about the glare right there. And we get a volume of NaOH, 10 milliliters. So that is how much NaOH we'll need to get to the equivalence point. Anytime we're before that, we're not to the equivalence point yet. If we go past that, it means we have extra base. Okay, so that is the number of milliliters to get to the equivalence point. Or milliliters to get to the equivalence point when we have equal moles of H plus, equal moles of OH negative, and we really would have water. So a lot of times, things that will be asked in titration will be, what is the pH initially of the HCl? So if we put a pH probe in there, what is it initially? What is it at halfway to the equivalence point? So when we've added 5 milliliters, what is it at the equivalence point, which we know for strong acid, strong base, because it will be 7. And then what if we go a little bit past? What is the pH there? And we'll sketch our titration curve here as we do this. So first part of this, when we have added 0 milliliters of NaOH, sorry, I didn't put that in there for you. When we've added no NaOH, what is the pH of this solution? Well, if you think about the pH of that solution in that case, there's no reaction. All we have is some 1 molar HCl. So that means the concentration of H plus is 1 molar because it's a strong acid, it completely dissociates. Negative log of 1 is 0. Our pH of the initial part in this is 0. So we know at the beginning of our titration, this is milliliters of NaOH added. We've added 0 milliliters. Our pH is 0. So we know our titration is starting right there, which is not normal. Usually you're going to start a little bit above that for a pH. Next part of this, halfway to the equivalence point. Well, we know 10 milliliters of base being added is at the equivalence point. So halfway, let's say we have 5 milliliters of NaOH of added. So we got a little, essentially an ice table here. Initial, change, final. We want to know in moles H plus. Well, we had 40 milliliters of 1 molar, so 0.04 liters times 1 mole per liter, 0.04 moles. That's how many moles are in there before we start reacting. So initially we have 0.04 moles H plus. We've added 5 milliliters of NaOH. So we're adding 5 milliliters of NaOH to figure out what the change is going to be here. So if we go 0.005 liters times 4 moles per liter, that is 0.02 moles. 0.02 moles of OH negative. So again, just figuring out the molarity there. So 0.02 moles of OH negative are being added. Now it's just stoichiometry. Limiting reactant is still going to run out. It's a 1-to-1 ratio. So we're going to go, this is going to go down by 0.02. This is going to go down by 0.02. This is going to go up by 0.02. So we have 0.02 moles of water, which we don't really need to worry about. We have 0 OH negative, 0.04 minus that, we have 0.02 moles of H plus that have not reacted. So half the H plus moles are reacted because we're halfway to the equivalence point. Half of them are still there. So if we think about our pH, we need to know the concentration of this, not moles, but concentration. So our concentration H plus would be 0.02 moles divided by our liters. Well, we mixed 5 milliliters of NaOH, and we had 40 milliliters of that. So we have 45 milliliters, which would be 0.045 liters. 0.02 divided by 0.045 is 0.44. Negative log of that. So do negative log 0.444, and our pH is 0.35. So pH should have gone up a little bit. It didn't go up very much. Okay, so after we have added 5 milliliters of NaOH, our pH only went up to 0.35. So our curve is staying pretty flat right now. Okay, pretty flat curve as we go there. Equivalence point. So when we've added 10 milliliters, let's go down to that part. going to speed this up just a little bit. So at our equivalence point, again, that's when we've added 10 milliliters. We figured that out before of NaOH. Our H plus initially is the same thing as it was before. Okay, still 0.04 moles. Again, that's the fact that we had 1 molar, and we had 40 milliliters. So 1 molar, 40 milliliters is 0.04 moles. Our OH negative, in this case, we have 10 milliliters of 4 molar. So 4 molar, 10 milliliters. So multiply 0.01 times 4 is 0.04 moles. Well, they're in the exact stoichiometrically correct amount. So these are both going to go down by 0.04. So both going to be 0 molar. We're going to have 0.04 moles of H2O made. Obviously, it does not affect pH. So we have equal amounts of these. That means that our pH is 7. Concentration H plus and OH negative would really not be 0 molar since they're water, and water slightly dissociates. Both these concentrations would really be 1 times 10 to the negative 7th. So really, really small amounts. All right, now we're just going to pick a number here. Last one is, what if we go past the equivalence point? What if we keep dropping in NaOH? That pH is going to shoot up really, really fast. So let's just pick a number here. Let's say, since we've gone by 5s, let's say 15 milliliters. And this is total, not like on top of the 10 milliliters here. 15 milliliters of NaOH. So again, this is 0.04 moles. If we go 15 milliliters of 4 molar, multiply those, and that is 0.06 moles. Now we have excess of this. This is my limiting reactant. We have excess of that. So we're going to go down by 0.04. Be 0. Down by 0.04 is going to be 0.02 moles of OH negative excess sitting around that had nothing to react with. 0.04 of them could react off with the H plus, and that much left over sitting around of excess. So if we want to get our concentration of OH negative over here, concentration of OH negative would be 0.02 moles out of our liters, which would have been 15 milliliters plus 40 milliliters. So 15 milliliters here, 40 milliliters of that, which is sitting in that flask the whole time, which would be 55 milliliters, or 0.055 liters, which is 0.364 molar. Give me 1 second. Negative log that, take 14 minus that, and your pH is about 13.6. So as you're drawing your curve, you start at the bottom, to curve it up there, your middle point would be a 7. It's going to level off up here at around 13.6. That's it.